We're probably all pretty familiar with cats, right? You know, generally 4 legs, fur, whiskers. I mean, we're on the internet after all, and even after all this time, the internet still loves its cats. There are a lot of different types of cats out there, and it's kind of wild that a little house cat gets lumped together with a mountain lion. Sure, they're similar in some ways, but also really different. Probably don't pet a mountain lion. Just saying. So a lot of the time when we're talking or learning about cats, we have to narrow down what we're talking about. For instance, let's say we're identifying a mystery animal. If we decide it's a cat, that's going to tell us certain details, like that it probably has sharp claws or a tail, but we still need to narrow it down. Like if we also know it hunts other large animals like many types of antelopes, now we're talking about a much smaller and more specific group under the cat umbrella. And we can keep regrouping our mystery cat to learn more about it. Because when we get specific about which group of cats we're talking about, we can explore those differences more deeply. And cats are just the beginning. With our set theory tools and the language of math, we can organize all types of things, people, concepts, and ideas into categories within categories in order to better talk about and understand the world around us. I'm Jason Guglielmo, and this is Study Hall Real World College Math. Last episode, we talked a lot about sets, which are well-defined collections of objects, meaning that we can definitively decide whether something belongs in our collection or not. So, the collection of all cats with 6 toes is a set, because either a cat has 6 toes, or it doesn't. Overall, math, and especially set theory, give us ways to clearly express and work with logical ideas. With precise language, they give us a way to easily organize a collection of things, qualities, people, and more, without any confusion about why we're grouping some of those things together and not others. So when we have a set, but we want to get more specific about the elements in that set, of course we have a word for it. In math, when we make a new collection out of a collection of things we already have, we call it a subset. Say we have the numbers 1, 2, 3, 4, 5, 6, and 7, and we declare that every time we see these numbers hanging out all together, we'll call them set A. Then, every time we see the numbers 2, 4, and 6 together, we decide to call them set B. Every element in set B is also in set A, so B is a subset of A. Or we could say that A contains B. In math, we also have notation to write this really efficiently, using this kind of sideways U with a line under it. And in formal math terms, we would say that set B is a subset of A, if and only if every element that's in B is also in A. So we can talk about sets to help us break our information into helpful categories or chunks, but we can get even more specific when we talk about subsets, and give them a name to make it easier for us to focus on whatever details we care about. For instance, let's say we want to explore the African diaspora, which refers to the movement of people from Africa to other parts of the world, both voluntarily and involuntarily, and their descendants. We could start by making a set that contains all the countries that are considered part of the African diaspora. But that list could get rather long, so we're going to set some boundaries for our set, which is a very mathy thing to do. So let's call our set AD, and say that it has all the countries that as of 2018 had more than 1 million members of the African diaspora. And it never hurts to do a self-check. AD is a set because either a country has more than 1 million descendants of the African diaspora, or they don't. Looking at our data from World Atlas, that would mean our set AD has 10 elements. Now, suppose the UN Human Rights Chief has initiated a program to attempt to protect people of African descent from further discrimination, violence, and systemic racism. For the pilot of this program, the UN will provide financial and non-financial assistance to people in countries where there are more than 5 million descendants of the African diaspora. Now, according to the World Atlas website, there are 4 countries that will receive that support first: Brazil, the United States, Haiti, and the Dominican Republic. And you might see where we're going with this. This is our first subset. But to be sure, let's check with our formal math definition. This new collection of countries is definitely a set because we have a well-defined rule about what gets included. Either a country has more than 5 million people descended from the African diaspora, or they don't. And each of these countries is in our original set AD, and no new countries are added. So we have a subset. We already know every country in set AD has more than 1 million people who are members of the African diaspora, but now we can zoom into the ones that have an African diaspora population of more than 5 million, and call this subset F. So instead of having to deal with 10 countries, we're down to 4. Which brings us to another characteristic of sets we can discuss, the cardinality or size of the set. For a finite set like the one we have, this is simply the number of elements it has. So set AD has cardinality 10, and its subset F has cardinality 4. Now, the UN can take this information and know what countries have a large African diaspora population, but also zoom in and know exactly how many countries to send reparations. Sure, UN officials probably aren't explicitly thinking about sets and subsets and curly brackets when coming up with policies around the African diaspora, but they are interested in these types of underlying relationships. From the examples we've talked about so far, it seems like subsets are just small chunks of a larger thing. And they can be, but in math we often need to be careful about special cases. For instance, let's go back to the set AD and look at what elements are in a new subset we'll call G, that contains all of the countries that are also in Asia. There's nothing there. Of the 10 elements in set AD, none are part of Asia. And this is where it gets kind of trippy. So let's revisit our formal math definition of a subset again. We said that some set B is a subset of A if and only if every element that is in B is also in A. And since there are no elements in G, every element that's in G is technically also in AD. So G is a subset of AD. So this is actually really important. In the world of mathematics, having nothing is worth talking about just as much as having something. When you have a set containing absolutely nothing in it, we call it the empty or null set. So in math terms, we could also say that G is the same as the empty set. So one special case is when our subset has nothing, but we can also have a subset that has everything. Well, everything from our original set. Like, say we have two sets that are identical in every way. They have the same size, elements, everything. These two sets are equal, which means that everything in one set must be in the other. So technically, by our formal definition, a set is also a subset of itself. That means AD is also a subset of AD. All the other subsets we've talked about today are called proper subsets because they aren't equal to the original set. And that can be important to know. Like if we said that F is a proper subset of AD, we immediately know that not all of the 10 countries we started with have African diaspora populations over 5 million. And we can show this with our notation. If we know F is a proper subset of AD, then we would write this using the sideways U without the bar under it. But if we weren't sure if F and AD are equal, we would write the sideways U with the bar under it, which means there's a chance F is equal to AD. Now, there's one more special set to cover. Let's say some UN representatives want to have a conference so they can figure out how they can best assist each country, region, and community they'll be sending reparations to. They want to create a schedule that allows each country to meet with everyone they need to, so they set out scheduling every possible combination. Hopefully it's not too many. First, they schedule a full group meeting with all 4 countries: Brazil, the United States, Haiti, and Dominican Republic. They can also schedule meetings that have 3 countries each, then all of the pairs, then individual time for each country. What we're doing here is actually figuring out all of the possible subsets within the set F. And what we end up with is basically a special set of sets, which we call the power set of F. The power set of any set is a collection of all possible subsets that could be created from the original set, including the special cases we just talked about, the empty set and the original set itself. Writing all that out, the power set of F contains 16 elements, and our UN reps would need to schedule 16 meetings. We can write this with our math notation too. Even though the elements of a power set are other sets, we take all of the groupings we just created and put them in between their own set of curly brackets and commas. We can also label a power set using a fancy P, and that immediately shows us we're dealing with a set of sets. Our set F had 4 elements, which gave us 16 possible subsets, but we could have done the same thing if instead we started with a set with only 3 elements, like the set of countries that are also part of what we now call South America. If we write out all the possible scheduling combinations of Brazil, Colombia, and Venezuela, we end up with 8 subsets. And spoiler alert, when we have 5 elements, there are 32 possible subsets. In fact, a pattern is kind of emerging. When a set has 2 elements, it has 4 possible subsets, so 2 squared. And when a set has 3 elements, it has 8 possible subsets, so 2 cubed. And when a set has 4 elements, it has 16 possible subsets, so 2 to the 4th power. The pattern keeps on going. Ultimately, the number of possible subsets is 2 to the power of the original set's cardinality, or how many elements are in it. We'll look for more patterns like this one in concrete examples later in the series. Like we said, the UN probably isn't thinking about their work in terms of sets and subsets, but they're navigating relationships and situations where the language of set theory can help us talk about the information we have. Mathematically, subsets help us get specific. We organize things based on similar characteristics or what they have in common to make it easier for our brains and computers to hold big amounts of information, so we can spend more time exploring other details. And cardinality and special types of sets and subsets, like the empty set, equal sets, or the power set, help us expand on the information we have, and build new ideas that help us learn even more. Next time, we'll keep exploring all that sets and subsets have to offer with set operations, or how we combine and manipulate sets to explore information and tell stories within data. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.